Okay, so as we continue with our parabolas quadratics unit, we're mostly talking about graphing. Now, having said that, your quiz today is just multiple choice, so as long as you can connect the visuals with the graph and identify some of these changing parameters, that's great. Again, we're using Desmos just because you're already on the computer, so it doesn't make a whole lot of sense to graph by hand every time. It's super tedious, and yeah, it's just a lot easier this way because we're able to change the graph in a dynamic manner. So, just as a recap of kind of everything the module talks about, because it's quite lengthy, the whole main point of parabolas is that they're nonlinear, they're curves, they can be up, down, they can have a min, max, so those are some of the values that we explored yesterday. And the key is your x has a squared on it. So, if I deleted the squared, it doesn't exist, there's nothing tied to it, but B, it would just be a linear function. So in order for it to be a proper quadratic or parabola, it must have a 2 attached to one of your x terms. This is called the base function. Some key properties that we already know from this is that our vertex is centered at 0, 0. Our a value is technically 1 in front of the x squared. So you'll notice that it's kind of going up and over by the same pattern each time, which we're going to talk about in the next video. But just first and foremost, from our basic properties, vertex is at 0, 0. If we, and I can type this one out, if we were to design a axiosymmetry, we know it exists at x equals 0, which is our x coordinate of our vertex. And we also know that our minimum point is at y equals 0. So this is symmetrical. We could copy and paste it out on paper, fold it in half along the line x equals 0, and it would be perfectly symmetrical. But what happens when we change parameters? Using Desmos is going to be the easiest way because you can just easily change any of the values and you'll be able to kind of almost spot the transformation right away. In your quiz, I would recommend having the Desmos tab open on one side. If you have a computer, just split screen it and you can actually just graph out the equations given and identify the transformations based on visual cues. So the first thing to discuss in the module is A. A represents your vertical stretch or compression. For simplicity, since we're in summer school, we're just going to talk about vertical stretches. So let's see what this looks like. If I take my base function x squared, I'm going to attach an a in front of the x squared. So let's say we do 2x squared. Okay, so notice how there's two colors. So the red is the base function and green is your transformed. So what happened there? Well, it was basically taken and vertically stretched up in a faster manner. You'll notice that you don't have the same points graph. So like on the red, you have a point that lies directly on 1, 1. Instead, you have a point, and sorry, it takes a second just to find it. You have a point at 1, 2. What does this mean? Well, it's accelerating the graph upwards at a faster rate. Okay. In other words, we would say that it's steeper. Even if it's up or down, technically the change in the stretch is a steeper one. Let's try something with a higher a value. So if we take y equals, we can even just do 3x squared. So notice that in the purple, even steeper. So if you were to describe the differences based on vertical stretch, okay, your narrower or flatter curve would be the red. In the middle is the green. And last but not least, purple is going to be your steepest. So what does this tell us? The higher the a value, the more it's rapidly going up along the y's as you move out by 1 unit on the x's. Some of the graphing in the module I find is a little bit trickier. I think doing it this way is much faster, it's convenient, and to be honest with you, just a little bit easier. So why not do it? The second component So that's A. You also have what's called translations. So you can have a vertical or a horizontal translations. The nice part about Y's is they don't lie. Only X's lie. So your vertical stretch is true to what it says. It took all of your points and stretched them by a factor of 2. Okay, almost accelerating the graph so that goes upwards at a steadier rate. Your K value is at the very end, so it could look like something like this. Okay, so instead of just having x squared, let's say it's x squared plus 3. So what you'll notice is it just translated the entire graph upwards on the y-axis by a factor of 3. Your stretch and everything is the same if you don't change the A value. It's just moving it up and down. So your new vertex would be at 0 and 3. If you instead use a negative K value, let's say we do -6, we're going to have to scroll a bit because now our graph is oriented around the point 0 and -6. Still has the same stretch. You'll notice that it still resembles the base function pretty well. All that's happened, we took the red graph, we pushed it downwards or upwards, depending on your K. So those two are more straightforward because Y's are true to what they are. The harder one is the horizontal translation. When you have an H value, you'll notice from the module that you have it contained in brackets. So let's say your H is 3. Okay, now X's lie. So technically it's X minus H. Okay, so your H value itself is actually 3. This is where it gets a little bit complicated. What you're going to do is flip the sign in the bracket. So see how it says X minus 3? We know a negative value along the X's is to the left. Just flip around your line of thinking and basically set that bracket equal to 0. Okay? Or easier, just flip the sign. So X minus 3, your brain initially wants you to say, okay, we're going to move to the left by 3 units. But X's unfortunately lie. So when you see a negative, it's actually moving to a positive value. So you are going to take that horizontal translation and it actually moves over. Again, since you're online, if you get confused by the H value, you could always use Desmos, a much easier tool than trying to hand graph it or figure it out with equation. This would be much simpler for you. Same thing goes with your positive H value. So what if it's X plus 4? Let's use different numbers. Okay, so same thing. A positive along the X's, you feel like you want to go to the right, but X's lie. So you're actually going to go 4 units to the left. Okay, notice how the vertex is now oriented around -4 and 0. So that's a brief walkthrough of the basic values of A, K, and H. In our course, just for time's sake, we don't explore horizontal stretches or compressions, which are super hard even to briefly understand. And we really don't need that for some of our exponential or parabolic functions because we're mostly using finance anyways as a means of real world applications. So what happens when you have all 3 transformations put together and how can you describe it? So let's take our x squared and leave it right there. And let's just put a whole bunch of different transformations on. I'm going to set my A value to 3. I'm going to open up a bracket. I'm going to put an H value in. Okay. Make sure that 2 is outside of your bracket. Otherwise, it's not identifying it as a quadratic there. And then plus 2. Okay. I'm using relatively small numbers, but just different ones so that you can see the transform function. First and foremost, you'll notice a couple things right off the hop. So the x minus 1 with the horizontal translation, you flip it. The opposite of negative is positive. You moved over by 1 unit to the right-hand side. Your K value, which is outside, it's the plus 2. That is your vertical translation. perfect. We went from 0, 0. We translated right by 1 unit along the horizontal axis, and we went up by 2 units, which is true to the k value. That takes care of 2 out of 3 values. The only other piece is your stretch. We can notice, I think, right away from the graph, it goes up quite a bit steeper, right? So it's accelerating at a much higher pace as you move over by x equals 1 unit. If we start from the vertex, we go over by 1, up by 1. Okay, so at the point 1, 1. The next video will go more into detail with the step patterns, so you might want to jump around the 2 videos. Here, we are starting at our vertex. We go over by 1 unit, and let's see how high we go up by. So we want to go to x equals 2, which is, and you might just have to click on it on the computer or identify it. So we went over from x equals 1 to x equals 2, and then we went up from 2 units to 5. The space in between is 3. That's equal to our vertical stretch of 3. You may be asked questions in the quiz related to yesterday's work and today's, just kind of combining your knowledge of characteristics of parabolas and your transformed functions. So how would we describe this from the base function? We would say our new vertex is 1 and 2. We are vertically stretched upwards by a factor of 3. We are horizontally translated to the right by 1 unit, and we're vertically translated up by 2 units. Something that is similar between both graphs, which is another question you might be asked, is what is the direction of opening? Both of these graphs hit a minimum value, and then they're essentially continuously going up forever. So that's important to understand. They are opening upwards, they have a minimum. If we put negative values on both of these graphs, and we'll just keep the exact same values just if we flip them around, notice that now that their a value is negative, they're both actually going downwards. So follow the true direction from the y's, because y's never lie. You have very similar stuff going on with your vertex. The only thing that's changed is your direction of opening and the fact that it is a minimum or maximum value. In this case, it's a maximum. Picture someone kicking a soccer ball. You start at one end of the soccer field, you kick it. Obviously, not everyone hits or kicks a ball in a perfect parabola, but let's just say you could. It hits a maximum and then it falls to the ground by gravity. Okay, so that is the basics of changing parameters in terms of transformations. To be honest, you could probably almost bypass a lot of the module, watch this and better understand. You can have the video open while you're taking the quiz. You could have Desmos and the video if you have the means of devices, whatever works, just so that you're successful on the transformations quiz. This module is split in half, so tomorrow we'll focus on the factoring and the factored form.